So in the previous video, I talked about the Cobb-Douglas and I gave you a quick way how to derive the Cobb-Douglas results. And I tell my students to always remember those Cobb-Douglas results, but quite often you are asked to derive the Cobb-Douglas through the Lagrangian method. So what's the Lagrangian method? Well, the Lagrangian method effectively says that you have an objective function that you are trying to maximize in this case, subject to a constraint. And what the Lagrangian method does, it says, well, I don't like a constraint. So I would like to deal with an unconstrained problem. So what the Lagrangian method does, it says, well, let's take an objective function, the Lagrangian, that it's a function of y, x, and adds a third variable that effectively captures that constraint. That will equal to x alpha, y beta, minus lambda, m minus px times x, minus py times y. And you might have gotten used to kind of setting up the Lagrangian, right? And the moment that you set up the Lagrangian, this becomes now a unconstrained optimization with three variables. So you go on and you do the first order conditions, which is to take the partial derivative of the Lagrangian with respect to x and set that equal to 0. Take the partial derivative of the Lagrangian with respect to y and set that equal to 0. Take the partial derivative of the Lagrangian with respect to the Lagrange multiplier, set that equal to 0. Now, this final thing here will always just give you the budget constraint. Right, so this is telling you that third equation, you must be on the budget constraint. Due to non-satiation, we're going to be on the budget constraint. Okay, well, what about this two? Well, these two are going to combine effectively, and I just want you to focus on this big picture here. This first order condition and this second first order condition, once you combine them together, you're going to go back to the condition that I told you, which is px over py is equal to alpha y over beta x. Okay, this is a condition that we derived in the previous video, right? So remember, this is that condition, right? Alpha y over beta x. Okay, so that's really what we're aiming to do, and then the rest is the same, right? So you're using the Lagrangian method, and really the trick is to use this first order condition, the second first order condition, combine them together to get here. Why do you need to combine them? Well, because you have a lambda that's going to be floating around there, right? So when you take the partial derivative of this with respect to x, okay, well, what you have here is you have the marginal utility of x, okay, because you're going to take the partial derivative of this with respect to x, okay? Then you're going to have here minus, or yeah, minus plus lambda px if you like. Now we could have also done a plus here if we didn't want to deal with that. It doesn't really matter on this particular occasion here. This will equal to 0. Okay, and in the second one, you would have margin utility of y plus lambda py is equal to 0. Right? And then you realize that once you send this to the other side, you have margin utility of x is equal to lambda px. Margin utility of y is equal to, sorry, minus lambda py. And then the final trick is you take this, let's call this 4 and 5, and once you divide 4 by 5 on both sides, the minus lambdas cancels out, and you're back to this equation that we wanted to, right? So I wanted to show you that if you had to do this with a Lagrangian, you end up to that same optimality condition, right? This is the optimality condition, or the tangency condition, but you could get there through the Lagrangian. And quite often you will be asked to do Cobb-Douglas, and quite often the examiners would want you to not go straight to the formula. And of course, if you just went straight to the formula, you wouldn't be showing that you've understood how you get to the formula. So you quite often have to set up a Lagrangian and do the steps to derive this optimality condition to convince your examiners of that you really understand this. I hope this helps. I'll see you on the next one.